Um, okay. Good afternoon, everyone, and good afternoon to those that are online. You are welcome to this lecture. This is day 2 of my lecture. Okay, so we'll continue from where we stopped yesterday. Okay. So yesterday we talked. So we quickly recap what we did yesterday before we move on. And today we will talk about solitons. These are special solutions of Ricci flow. We will discuss about them and maybe just give some examples. Then we'll discuss short time existence of Ricci flow. We said yesterday that Ricci flow is a partial differential system of partial differential equations, and we want to see a system where you have a partial differential equation. What is most important is to have existence results. Okay, because of example we gave yesterday, we see that at some point the Ricci flow will run to singularity. Then we need existence results at least for short time. Then we will discuss evolution of geometric quantity as the Riemannian metric is evolving. When you are running the Ricci flow, every quantity related to the geometry is also behaving in one kind, although that we are going to see the way they behave. So in what we discussed yesterday, well, what took most of our time yesterday was the basics of Riemannian geometry, where we build our smooth manifold from a topological space. We saw how okay, when you have a topological space, you put your charts on it, then you have a topological manifold, and if you can cover the topological manifold with as many charts as possible, you get the maxima atlas, then the transform map. We discuss all those. When the transform map is smooth, then you have a smooth manifold. Then we talk about metrics, Liouville connections. We talk about curvatures or manifold. And we say when you have Riemannian metrics and the smooth manifold, then you have Riemannian manifold. Then we went ahead and to introduce the Ricci flow equation. We gave the Ricci equation in a simple form. Then we just describe the quantities you have in the equation. We give examples. So we give Einstein metrics. If you have an Einstein metric, you start your Ricci flow with an Einstein matrix. Okay, we have the kind of solution you have. And from there, we build, when you have a shrinking solution, you have a stationary solution, expanding solutions. We even saw that Ricci flow preserves product of matrix. Okay, and some other properties of Ricci flow that we talk about in our yesterday was a scale invariance of Ricci flow, Davos invariance. We said Ricci flow, as you have your Ricci tensor, does not change other scale invariance, does not change other Davos invariance. If you have a pullback of metric, okay, then the Ricci curvature of that pullback is also just the pullback of the Ricci tensor of that matrix. We saw that, and then we discussed about Ricci flow on surface. Maybe let me give us some things and to start from Ricci flow on surface that we said. We said on surface, two-dimensional manifold. Mentioned yesterday. Okay, I'll start like this. This is our Ricci flow. We give description of this. Okay, we now say if this is a n-dimensional Riemannian manifold, if you have n-dimensional compact, okay, in this case, let's just say without boundary. Okay, dimensional compact manifold without boundary. We define Ricci flow as this. Then if the dimension is 2, this Ricci curvature is written as, we said, Gaussian curvature, dimension it, multiplied by the metric. That is in that dimension. So we denote this as K. Then we now say, okay, our Ricci tensor in this is KG. So that we write this equation. Okay. We write this equation as minus KG of T. So this is what we got yesterday. And we say, okay, if you have this, if you start with a manifold with K here is constant. I use kappa. You say K is constant kappa. If you start with that, then we have this as solution of a Ricci flow. We got this and said from here, we cannot just write our Ricci flow as this. This is kappa GT. Okay. And from here, we said, oh, you have this. Then the behavior of Ricci flow depends on the sign of the curvature. If you have a surface in this dimension, then we give this, we will have a kind of, yeah. Okay. Say this is just S1. If you have where the curvature is positive and where the curvature is negative, we said the flow strengths, where the curvature is positive and where the curvature is negative, then the surface invariates. So this is what we discussed. And we said, okay, if K is, not K, kappa, greater than 0, in this case, you have T in this region. Then the solution strengths. The solution strengths, if kappa is 0, then the solution exists from this interval. So this is a metric. In this case, matrix does not change. So that is it remains stationary. Matrix doesn't change. So you have a stationary flow. And in case kappa is negative, then to plus infinity. So you have this, the solution expands as a T. Okay, let me see, as T goes from here to infinity. Okay, that is when T, the solution expands. If the solutions converges to this from 1/2 kappa from negative, you have the metric in this case shrinks. So we give this kind of result in dimension 2 yesterday. Okay, so then briefly before we go on today, let me quickly mention our classical result that we have in dimension 3, original result from the work of Hamilton in 1982. Because I said yesterday, I mentioned it briefly that Ricci flow was originally designed to solve problem in dimension 3. So this is the result. Okay, in 1982, you got this. So if you have a 3-dimensional closed manifold. By closedness here, we mean a compact manifold without boundary. If you have that, then Ricci flow exists up to the time that we call T-max. Anyway, here we have not talked about existence, but we are going to do that. This Ricci flow exists up to this time T-max, which is a finite time. So if you have that, as time approaches this finite time, that is the maximum time of existence, then the result says the diameter of the manifold collapses. If the manifold is a three-dimensional with positive Ricci curvature. Okay, so one of the following, in fact, all these three items here happen. One, the diameter of the manifold collapsed, or you have the limit T max of a sectional curvature of T over this, it becomes 1. Then 3, you rescale the matrix, this form converges to smoothly to a limit matrix. So this theorem, in fact, asserts that in any three manifold with positive Ricci curvature, it behaves asymptotically along the Ricci flow, just like a round matrix. Okay, the diameter, when the diameter collapses, we see a round matrix yesterday. When we give that of a round matrix, we said you have this one as an example. It collapsed up to a point as t goes to this particular time. I think we got 1/2 lambda that yesterday. It collapsed until you get a point. So the Ricci flow collapses round matrix. So you have a replica of that in dimension 3. So the research says that, okay, when you have that, then every such three manifold that admits that round matrix is topologically X3 or quotient of S3. So this S3 here, this gamma is just an isometric group active freely on an S3. So telling you that every three manifold with a positive Ricci curvature is diffeomorphic to either S3 or quotient of S3. So the next slide. Let's move to the next slide. Okay, then we have this standard result also. Okay, let M3 be a closed three manifold, and you have non-negative Ricci curvature. Okay, the Ricci curvature, you start here. This is the initial metric you are starting with. Okay, with a positive Ricci curvature. You run this with Ricci flow. This, you have one of these results. If you start with a metric three-dimensional manifold with non-negative Ricci curvature, that is Ricci of G0 greater or equal to 0, then one of the following arises. 1, Ricci curvature of the GT, this is now Ricci flow, is positive for any time t greater than 0. Then M3 is a spherical space form. It's a spherical space form. That is a three-dimensional spherical space form. Then you can have Ricci curvature, okay, degenerates, becomes 0 or equivalent to a flat metric manifold. So you can have this. Also, you can have Ricci curvature never becomes strictly positive or identically 0. Then locally, it means this M3 splits into this surface with a line, okay? And this is a surface with positive curvature. This, you have the surface of positive curvature with line is in dimension 3. So this one look like Poincare cylinder that we read yesterday. If this one has positive surface, this surface has positive curvature with this line, look like a string cylinder. that we gave this, for example, S2, sorry. This is a two-sphere, and when you have Ricci flow on this, we have okay, to have this right perfectly. Then over time, it becomes something like this. And a particular time, it turns to a line. And you just have this. So this is what we call shrinking cylinder. From this cylinder, it becomes just a line. So it's contracting the sphere while the line remains stationary. Okay, so these are the results of Hamilton in 1982. Okay, let's go to another special solution of a Ricci flow, which is called Ricci soliton. Ricci soliton. In fact, this is a larger class of self-similar solution. In fact, than uniformly shrinking or expanding solution that we just discussed. In fact, this shrinking, expanding, they fall under Ricci soliton. They are special solution. Ricci soliton is very important, very central. In fact, let me say fundamental to the study of Ricci flow. They serve as model to study singularity of Ricci flow. These are special, and we're going to discuss. Let me just give definition, then I'll give examples so that we can move forward. Okay, so let's, by definition, we are going to start. Okay, let me put this one. In this case, we want to modify flow by one parameter group of diffeomorphism, and then we define a time-dependent vector x from it. We mentioned yesterday that you have a vector field here can generate a flow of diffeomorphism. So let's write T, okay, T in this interval be a smooth family of diffeomorphism, time-dependent diffeomorphism now, okay, between from M to M. And then you divide GT, okay, time in this, you have time in this interval is a smooth family of Riemannian metrics on M. Given a smooth scalar function, this one is a scalar function. So we'll call GT, okay, this is a Ricci flow. This equation here is supposed to be a Ricci flow. This GT is a Ricci solidon if it is a pullback of this initial metric. You have a pullback of this initial metric, then that can be shown easily. You have GT, and you have a real value function beta t. Then you have a pullback of the initial metric. Then this is a solution of Ricci flow. And what does this mean? This means that in the Ricci solidon of the Riemannian manifolds are isometric up to a scale factor that is allowed to vary with time, okay? And from here, we can, the Ricci flow equation now, the Ricci soliton equation is equivalent to this. Let me quickly show some computation here. That would be better for us. If you have this, to show that this is a solution of a Ricci flow, okay, let's find the evolution of this. Then you have this. And meanwhile, in the definition of this phi of t, if you have phi of t here from M to M, you add additional that phi of when t is 0 is just the identity M. So here you can just find that, and what do you have in this case? Here, you differentiate this, you have beta prime of t, okay? This G naught is what you start, does not depend on time. Then you have beta of t, then okay. So this is what you have to do that. If you want to do this now at t equal to 0, then this becomes a scalar number. You can have this. Then this is an identity, and you have B naught here. Okay. Then this time, this one gives a Lie derivative in the direction of the vector field generating this diffeomorphism. Okay, that is from the definition of diffeomorphism that we discussed yesterday. So in this case, having this, can just move down here. So it is easy to just arrive at this equation, okay, which is a Ricci-Soliton equation. And the Ricci-Soliton equation is given this way: Ricci G naught plus half of Lie derivative in the direction of x G naught equals to lambda of G naught, where you have lambda now. So in this case, well, this lambda, if you compare, if you solve this and you get that line, the lambda will be taken as a minus 1/2 beta prime of t. Okay, so x there, which we have just, is just the vector field which generates this. And by definition, if you have a vector field generated by this x, we define it as this vector field S composition with phi t. So that is how we arrive at what is written as equation 1 here. So this is Ricci-Soliton equation. Now, this Ricci-Soliton equation is given in terms of this vector field x. But in case the vector field is not given in terms of a gradient of a function, you have a function f on M, a smooth function which is called potential. So you have a potential function on M. Then this x, suppose it is given as gradient of this f. The equation that we have the other time, this equation, okay, if you recollect, we have this guy as this. By definition, Lx of G, we define it as a 2 Asian, sorry, please. Okay, we define this as a Asian of function f. Okay, from the definition that we give for Lie derivative in direction of this. If you have f as a smooth function here, this Lie derivative is expressed as this. So if you have this into this equation, then you have equation 2 there, which means you have, sorry, you have the first equation, not the equation 2, the first equation like this. This, if you put this one here, this is what you have. Ricci G naught plus this guy is this, with this half. That is Asian of f is equal to lambda G naught. So we have that. And that is, okay, if I put, so in general, it may not even be, because you can even do this soliton with that Ricci flow. So in general, it may not even be G naught, it may be G. Okay, So that's what you have if you don't put G. But in the case what we are doing here, G naught, you can just say G naught, G naught. So, and that is what we have here. So this equation now is gradient Ricci-Solidon equation. Gradient because you have expressed the vector field here as a gradient of the function. It is called gradient So in general, if you have a manifold with matrix with the vector field here, you can say this metric or this manifold is a Ricci-Solidon. If the following equation holds, so you have Ricci of G plus half lead derivative of G equals to lambda G. Okay, and you call it a gradient Ricci-Solidon if X is equals to gradient of a function f, where you have f as a smooth for m. So in that sense, you have Ricci of G plus Asian of f equals to lambda G. Okay, so that's what you have. And you have this lemma. This lemma says, if you start, you have this pullback metric rescale with this scalar function, okay? And it's a Ricci flow, which we have shown earlier on. But if you have this as a Ricci flow, then there exists a vector field X on M such that you have this, okay, which we have already we already showed. Conversely, given any solution this of these two, then there exists a smooth family of diffeomorphism on M and scalar function B is such that GT is a Ricci flow. Okay, so what this is saying is that if you have a Ricci flow, you can get a scalar vector field to arrive at a solidon. This is a solidon equation. Or if you have solidon equation, it also gives rise to Ricci flow. So it's just one way you start from, you have a solidon. Okay, if you have a soliton and you get we define that a Ricci flow is invariance under rescaling. If you now rescale here with a scalar function here, BT, and with this diffeomorphism, okay, let me say this way. Ricci soliton is invariance under scaling. It's also invariance under group of diffeomorphism. Now you now have combination of a scalar factor here, and this diffeomorphism, you rescale here, then you see have Ricci flow. Okay, so that is what this, and it's just computation. The proof is computational. Yes, you can show geometrically move from one manifold. Okay, you have a manifold where you build this, and another manifold. Okay, the same manifold. You have your G, okay, and then you put a background. If this is the diffeomorphism, from here to here, you can get a pullback of this metric, okay, and you have this pullback of this metric as a phi t star G naught. So if you rescale this with a time, a scalar function. Property of Ricci flow says the metric you get by this is also Ricci flow. So if you have this, you get a soliton. This is an example of a soliton. In fact, this is where we start the definition of a soliton. So you have that. And then if you have a soliton equation, you can get Ricci flow, give rise to Ricci flow. Okay. So next. So the proof is Okay, let's move to next. Okay. Before that, let me give us some example of Ricci. There are some things, important facts I want us to just note here, which we need to know, because it will help us in the later part of this course. This theorem, well, can see this theorem, there are facts I want us to know. One, I want us to know that if you have, okay, I think I mentioned here that this lambda we have here is scaling parameter. If it's less than 0, okay, if it's less than 0, you're negative, you have expanding solidon. Okay, if it is 0, you just have this, then you have a steady solidon. If it is positive, lambda is positive, you have a shrinking gradient Ricci solidon. Okay, so with this fact here, Ricci solidon is as time if x vanishes. If x vanishes here, you know this term becomes 0 because this f, gradient of f is x, and x vanishes. So you don't have this Asian structure here. So you have just this equals to lambda g, which is the same as Aston equation that we discussed yesterday. So here, if you have a closed, sorry, let me just say expanding under our M is closed. Okay, if you have expanding or steady soliton, okay, let me put this way. M is closed. Then here, all these I want to mention are as time. It's better this way. So which I'm not talking about expanding. That is soliton. Okay. Taking three-dimensional solitons. So you have this. And of course, we can even construct example in Euclidean. Euclidean, for example, is example of solid, or maybe I'll give that as another example. Sorry about that. Let me just give us this example. Yeah, this is Euclidean solidon. So here you can have Euclidean space. It is canonical metric. is the steady soliton. So you have here, and you have the Euclidean metric, okay, on this. Then this is a canonical, this is a steady soliton. And from here, you can even build a potential function on this. If you build a potential function, say this lambda over 2 x squared, this is a potential function of this. You have this with f so you have this, okay, as a soliton, which can be shrinking, steady, or expanding depending on the value of lambda. So this is an example in Euclideans. So for a good example, we have good example just like this Seeger soliton in dimension 2. We have Bryant soliton, okay, in dimension 3, okay, when you have ferrotinal symmetric. Okay. Yeah, let's move on from here. We want to see Ricci flow. We are to now as a differential equation. I think this is very important now. We are getting to seeing Ricci flow as a partial differential equation so that we can see if theory from partial differential equation can be ported to establish existence and uniqueness of Ricci flow. So the first point of call here is let's see Ricci tensor. So this, I just put it as a corollary. I put here, so we do some things, then this is the corollary of what we are going to do. We are going to express Ricci tensor, and maybe in local coordinate now. If you express Ricci tensor in local coordinate, it is minus half times Laplacian of a metric tensor plus some other term. So that Ricci flow that we have this okay, that we have this as this will become minus 2 become this plus lower order term. So meaning that dt just look like a Laplacian of g plus some other term. Let me just say q, g, you have g inverse and first order derivative of g. So this one look like a reaction diffusion equation. If you compare this one with a normal heat diffusion on manifold, which we call heat equation, this look like it, but you have the nonlinear term added to it. So this is a reaction diffusion equation. So that is the essence of looking at this. So we are going to see how we can express the Ricci tensor to look like this. So that is the next thing we want to do. So, okay, let's from here. In harmonic coordinates, Ricci tensor is what we have as equation 3 on our screen. Okay, let me write it here using Einstein summation conversion. So this, just because of what I typed the other time, this Rij is the same thing as this. I wrote it as this in some other places. So this guy is okay. After summation conversion, the summation there, I just want to remove it. Repeated indices is summed. It's summed up. So I have this, according to what I have on the board, partial I, partial J of GKL minus partial I of GJK of GIJ. Okay. Now plus lower data, for which we don't need to. So this is a grid tensor. Now, this can be seen working in local coordinates. So, which we can easily, let me give us out to, if you want to solve, if you want to rewrite this, a way to do that is writing this Ricci coefficient in terms of a full Riemannian coefficient tensor. So we recall that you have this guy, okay, as this. Let me just quickly write that. This Christopher symbol is given as this. Minus so this, you know that. Then that was a lemma that I showed yesterday. We didn't we just gave it that Rij Lk is given as this. Okay, so you have this. I think IGL, yeah, GLI. Okay, so you have this. Then, if you have this, you can write Rijkl in terms of this GLP. You can lower the tensor here. That's the meaning, using this metric. So you have this. And the Ricci tensor Rij is just the metric trace of a full coefficient tensor. So you have that. And which is just this over this GKL, GLP, Rij, LK. So you will be able to write this in terms of Christopher symbol. Okay, because this already we know in Christopher symbol. Okay, by the time you trace, you lower the index here and you do the tracing, then you have a nice expression of Rij in terms of a Christopher symbol, and you will be able to differentiate. Oh, sorry, you'll be able to substitute the value of this in that expression. Maybe we quickly write that down. It's a long calculator, but let's write so that we see it. So from there, you will now be able to see that Rij is okay. So you have this expression here can be written from here. You do the lowering of the index, okay? Then you do the tracing to contract. After that contraction, you have this Rij. And then from here, you put in. So this is the expression that we have for that. And here, once we know this, if we substitute here, then we reduce to finding this derivative of this Ij from the value here. And then you see some terms, because we are working in local coordinates, you'll be able to change index, you'll be able to, by the time you change index, some will add up, some will subtract, and what you are left with is going to be this expression. Okay, in local coordinates. What is a local coordinate, which is very, very important? Maybe we should mention this. By the meaning of local coordinate, harmonic coordinates. Let me write that so that in harmonic coordinates, here we okay, on n harmonic coordinate on an n-dimensional manifold is a set of local coordinates I from 1 to n, okay, such that you have this of this x equal to 0 when you have I from 1 to n. So this is a definition of harmonic coordinates. So when these coordinates are local coordinates harmonic, then you have this. This is Laplace Beltrami operator. So if you have that, you can, this guy that we wrote up here, the Laplacian there, this Laplacian is written, okay, okay, a local coordinate is this. Okay. Then if you come to harmonic coordinates, you can check Gij of this, which will give you some terms, and we show that the lower order term that you're supposed to get as a result of this vanishes. All of them vanish, become 0. Okay. So in fact, this look like a 1 over root. This is what you have. This is the determinant of the matrix. By this. And oh, sorry, something is here. GKL is G. Sorry. I think this should be here. You have none of this partial L of ELP. So this is what you have. So this one shows that you have all the lower term that you're supposed to have. They'll become 0. So this Laplacian easily becomes Gij partial I partial j. So this is what Laplacian is in that coordinate. So if you now come back to this, if after we have solved, do our simplification from here, we find the derivative of this when we substitute the expression. So this term resort to the lower terms that you have. But in harmonic coordinates, as we have shown here, those terms vanish and you arrive this. So from here, if you look at this, in fact, this is ij, this kl here, this look like the trace. This is like a Asian, this is Asian, this is like an Asian of the trace. If you change here as well, this also like a Asian of trace, this like Asian of trace, GKL, partial K, partial L. In fact, just like Gij, partial I, partial J that I have here. So this look like this is Laplacian, definitely. So from here, this gives the lower order term, and this one gives Laplacian. So all this what you have here is like a Rij equals to this give the lower order term, then this with this give -1/2 Laplacian of Gij. So with this, we have this of G that we tend to prove to be -1/2 Laplacian of Gij, then plus lower order term. So that is what we have. And with that, the Ricci flow can be written Ricci flow cannot be written as this, which shows that Ricci flow is a system of nonlinear partial differential equation. So the question now is, does it behave like a diversion of it? Yes, of course. But what you have here, and because of the diffeomorphism invariance of Ricci tensor, this guy here, it is not uniformly elliptic. It is not, let me put, yeah. Okay, anyway, let's say this symbol here, maybe we should move on. Let's go to the next slide. We will discuss it when we get there. So let's move to the next slide. Okay, good. Okay. Okay, maybe we should discuss this as before we move on. Diffeomorphism is invariance. Okay, others this diffeomorphism. That is, I mentioned it the other time. If you have a pullback of metrics, you have the curvature of a pullback of metric. There is just the pullback of the Ricci tensor. Okay, that's what we mean by invariance of that group of diffeomorphism. Also, yeah, if you define GT, I mentioned the other time, this is still on the board. If I define GT to be, if you have, I have a pullback of, I have a background metric, then I pull it back. Okay, I pull it back, the new metric I have is also a Ricci flow. So that's what we mean by this one. So you have that. And that one gives all these infinitesimal properties. If you have Lie derivative of matrix here, this derivative gives, let me try to give that explanation here so that it looks meaningful. Okay. So if you have this phi t as diffeomorphism, okay, t here means phi is a time-dependent diffeomorphism. Good. Now, Ricci tensor of a pullback of this metric. This is a pullback of this metric is just the pullback of the Ricci tensor of G. Okay? And that if you now have GT is a Ricci flow, then the pullback of GT is also a Ricci flow. Okay? So also the pullback of this is also a Ricci flow. So that's diffeomorphism invariance. Now, if you now have, show that you express this just like what we did the other time, okay? So you have, let's give us this before we move to this. Let me give this. This gives this property here. Sorry, please. This property here gives, okay, say phi t is generated by a kind of vector field X. Then this gives a kind of variation of this S of Ricci tensor this. Let me say Ricci tensor of, let me use S now, of G. So this is G of X. Do this at S equal to 0. This is just a variation. And let's take delta as variation of that of Ricci. It gives us Ricci of G of the Lie derivative of G here. I mean, in the direction of X, which is the same as a Lie derivative of Ricci tensor. So having this type of this expression from here, then what we have on the board, we can have this. Okay, so this is a pullback of the metric. Now we are writing it in terms of this Lie derivative in the direction of X. So this gives, and if you have from Ricci flow, yes, Ricci flow from Ricci flow, derivative of G is -2 Ricci. So this is now giving us this -2 and the variation of this. Sorry. So that's what this, and from here, from that, this equation that we have on the board here, then it shows because of this, the effect of this diffeomorphism, okay, this is not going to be strongly parabolic, okay, because the elliptic operator, the operator we have here is not going to be strongly elliptic. So we are going to show that maybe in the next slide. Okay, this is just linearization of the Ricci tensor. Okay, if you do the linearization, take variation of G to be H, and do the linearization, this as S go to 0, the variation of this, just like what I have here. And we already have the value of Ricci as what is on the board, what is up here. Okay, if you use that, that's how we have this expression here. And this variation is a differential operator from this space to this space. Okay, and this is what is going to call a principal symbol. Okay, in the direction of this vector. We are going to discuss this. Maybe I should just skip this. So if you do that, then you are writing this Ricci variation of the Ricci in terms of certain differential operator, which we have just shown. Here, we said this will give us the Laplacian, which is here, if the variation of G is H. So this is what you have here. And this is the Hessian of the trace of this HKL that we have there. That is why you have HKK and the other terms. So this is now a differential operator. If this is a differential operator, we represent it with L. What can we say about this L? So that is what we are going to see in the next slide. So before I mentioned the principal symbol there. So before we know that, let's go to PD theory. So that when we build that from a partial differential equations, then we'll be able to talk about short time existence using that idea. So the main purpose of this is that we want to use the idea of PDE to prove existence of Ricci flow. And to do that, we want to see if it is the theory we want to use the standard theory from elliptic theory. And we want to see that the elliptic, the diffusion operator we have here, the Laplacian, is elliptic. So that is the idea. And before we understand that, we want to take ourselves to theory of PD. Okay, I will quickly discuss this. Now let's consider second order partial differential operator. Yes, in Euclidean, you have this, where this L is the general second order differential operator written as this. And from here, okay, this is just notation, which we have mentioned. If you have partial IU here, is just a direction derivative, differential operator is the direction of this I. Then there are some conditions on the coefficients here, the Aij, Bi, and C. So this Aij, you have their smooth coefficients. So this L is a second order partial differential operator. And we say this operator is elliptic if you have this. Okay, where you have this Euclidean vector xi in R. If Aij, which is a symmetric smooth function here, is greater or equals to lambda epsilon this vector. Okay, if you have this Ij psi, then you have this norm of this vector square. So this is positive. This is greater or equals to this for positive lambda. So if you have this expression from the here, then you say this operator is elliptic. And if L is elliptic, then you say this equation 4 here is parabolic. So that is why you write, that is when you can now say so if L is elliptic, okay, then we now say B this operator we say is parabolic. Okay. So an example is heat equation. If this L is just this, if you have heat equation in Euclidean, if you look at the operator L that we have here, okay. Now let's say Bi is 0 and Z of X is 0. So these last two terms become 0. So you have the first step here. This is just Laplacian in Euclidean. Okay, if you have this Laplacian in Euclidean, we know that when you have this, for example, you say U equals to something. This is an elliptic equation. Okay, if you have this, this is a parabolic equation, maybe equals to some term. So, and that is just example in Euclidean. And we can even put this have a replica of this on manifold. Okay, so we have the equation now on manifold, where you have this operator, okay, from this space to this space now. Instead of Euclidean, you have M, but in our case, we keep M as a closed space. So you have this, and this L is just written that way. So also, we talk about elliptic and the parabolicity of this operator and operator with time dependence. So just like we mentioned. And if you have that, then you can now talk about existence of solution. So if this is a parabolic, or if this operator L here is elliptic, and you have a parabolic equation, then there's a standard result, which say solving this initial value problem, then there exists a unique solution for this system, for this equation, okay, with this initial value here. So this is standard result from a PDE. Now, if you look at this term, from here, this ellipticity that we discuss here, it has to do with the highest order term, okay, highest order term. So we want to talk about total symbol and the principal symbol. So this higher order term, we define what is called the principal symbol, and all the old time is a total symbol. We'll see it next now. Okay. In our case now, let's say we consider linear differential operator on the bundle E and F. Okay, we write it like this, where alpha range is the absolute value of alpha is less or equals to K. So where this operator is just a bundle homomorphism, okay, alpha is a multi-index. So this is a differential operator. Now we define total symbol. Total symbol now, if you pick a vector xi, okay, in the bundle, then you have this operator. This sigma here is the total symbol of operator L, given as the sum of this sum. So which means you sum all the terms of that operator. So this is called total symbol. And if you take only the highest parts, okay, under this symbol should be this will be for alpha equals to K. Yeah. So for this symbol, so K is the highest order derivative you have here. So that is a total principal symbol. Yeah, this is just example I mentioned the other time. If you have L, now we are on the manifold. Okay, on the bundle, L is written as this. The total symbol using this psi, this vector psi, is this. This is total symbol. But for the principal symbol, you have it in the highest order derivative as this. Okay. So when faced with a nonlinear partial differential equation, one attempts to linearize the equation in such a way that linear theory can be applied. If you have this equation, since this a linear partial differential equation. Okay, this operator P moving from here to here is a quasi-linear second order differential operator. And locally, when you work in local coordinate xi and use local frame ek on E, it can be written as this. Okay. And in fact, I put in red here that a Ricci flow equation fits into this category. So Ricci flow equation is a quasi-linear PDE. Now, given an arbitrary fixed section eta, we say that C is parabolic strictly if the linearization of eta is parabolic. Okay, if you recall the way we defined there, we said if the one operator is elliptic, then the time dependent is parabolic. Okay, so here now we are doing linearization of P. This P, if this is a non-linear. I've given an example in terms of linear. This is non-linear. We are now going to do linearization of P. That's what we do in PDE. If this linearization is elliptic, that means the whole thing is parabolic. Okay? So the linearization of P is dp eta. If this dp eta, okay, is elliptic, then the equation is parabolic. And you have the theorem. Once we establish that this is parabolic, then you have to say that this equation, if it is parabolic at eta, then it has a unique solution in this interval. Okay. And the coefficients, well, these are the coefficients of the highest order derivative. Must satisfy certain condition, some regularity assumption of this ij, well, which is not of interest to us here. We are just trying to build this. Now, if we now consider Ricci flow, yeah, okay, I denote it as a Q now instead of P that I have the other time there. So this minus 2 Ricci, which is which we want to be elliptic operator here, and we denote it as Q. Then we can linearize it. It gives this, after linearization, it gives this line. And from here, we can check the principal symbol. So the principal symbol, it is the highest order derivative, GKL with HKL, the first one here. This other one is the lower order time derivative. Then the linearization of this gives this bundle. So you now have, if you replace this covariant derivative, partial I, partial J here, with this cofactor, then the linearization in terms of this cofactor gives this line, the last line on the slide. So, and looking at this, having computed the principal symbol of linearized Ricci tensor, we can now check whether or not it is elliptic. Okay. For this to be elliptic, it requires this one to be greater than 0. That's the meaning here. But here, if this HJK that we have in the previous slides, HJKL, HJL, HIL, here that we have in that part, if we replace it with psi j, psi k, this vector, then what we have here will vanish. It will be 0 instead of a greater than 0. Because originally we said if you have operator should be Aij, psi I, psi j should be greater or equals to lambda psi square. Okay. If you require lambda is taken from R. If you require lambda to be 0, we expect this type of thing to be greater than 0. So we are expecting such thing here. But like what we have, these higher other derivatives that we have here. Okay, so this is the Laplacian. These are the Asian of trace. By the time you put this pk here, and they are also second order. So this is the highest order. By the time you replace this h, this tensor h with psi I, okay, this one with psi k, psi l, this one with psi j, psi l, then this is what you will have. So meaning that the Ricci tensor is not elliptic, and the Ricci flow is not strictly parabolic. Okay. So that's what we have here. So with this, it will be difficult to use PD theory. And that was why in 1982, Richard Hamilton used theorem from functional analysis, Nasmussen implicit function theorem. Okay, that's what he used because the flow is it's not strongly parabolic. But later, the talk, okay, use his own trick. Then is the talk in 1983 after the papers have been seen. He used a way which is now known as the talk trick. He constructs, because we have seen that non-parabolicity of Ricci flow is due to dimorphism invariance. Okay, he now use a way to modulo out the dimorphism invariance from Ricci flow. He got another flow, which is known as anyway in this course we call it the talk Ricci flow. And he was able to show, this is just the way to do, he was able to show that after he modulo out that diffeomorphism, he got a new flow, and he was able to show that that flow is strongly parabolic, and he used standard PD theory. So the problem now remains, how do you now convert the solution of the new equation to talk Ricci flow to original Ricci flow? Okay, so that is what these are the motivation for doing that. Because from the explanation I showed on, we saw what exactly constituted non-parabolicity for that Ricci flow. And that's okay, if this is what is causing it, the diffeomorphism invariance, can we use a known kind of diffeomorphism between manifolds, okay, which satisfies certain equation, and the equation is called harmonic map heat flow. There's a standard existence result for that. He used that to do a conversion of, to modulo out the diffeomorphism from the original Ricci flow to get his own flow. And this is the idea of things that these are the steps involved in doing that. So, well, let me explain back here. So after that, he defined this motivation. We have this kind of derivative, which with a Li-Yau connection. These are Liouville symbols, the coefficient of Li-Yau connection. Okay, this is well defined. Of course, it's difference of two connections, and it has a new operator. Okay, from here, and this operator is given by the Lie derivative of G in the direction of this W. So if you go back to what we did the other time, the diffeomorphism is called by the Lie is generated by vector field, which can be written in terms of that Lie derivative of that vector in the direction of that vector field. And now it has this idea. So, and if you see that linearization of this operator here, which is this guy here, is a second order differential operator, then the linearization gives this. Okay. So where this V is a vector. Okay. So this is what you have. Yeah. And you move down. This cannot lead us to consider a new operator, which I put par. So Q here is already, I defined this one as a -2 Ricci, tensor of G the other time. Then this P is the new one that we are introducing, which is in form of that Lie derivative. Okay, so which means This Q bar will be minus 2R minus 2 Ricci tensor plus Li derivative. Okay. And then we cannot define new flow in terms of this operator. We now say, okay, we flow GT to give Q bar. So which means we are having new flow, which is a d dt okay, I have a new flow which is d dt of G, okay, number equals to Q bar, which is minus 2 So this is also different of this. So this is the new flow that we have. Okay, so this is what is called Ricci flow. You can put the initial condition and a little linearization of this operator. So this linearization of this, we take care of the deformity that is coming from the linearization of Ricci, and what you have is going to be linearization of yeah. Okay, so where this Aij is just first order linear term. Additional, I mean, the first order linear term coming from a linearization of Q, and the one coming from linearization of P is what I denoted as this. So this linearization of Q bar gives us Laplacian of H, and this is first order term. So which means we are left with this as the principal symbol. So you cannot do here, when you write this, this becomes okay plus lower order term. So this linearization, this is a Gij partial I partial j of, let's say this H is Hij. So if you substitute, you want to find this of this operator, which we have written in the example given the other time. Let me just put this way to show us. So this is what we are going to have. We just have psi square H. Replacing this Hij with psi I, psi j. And this vectors here is psi I, psi j. So you have this. So, well, maybe, yeah, that's okay. Let's just replace this. And if you replace Aij, then it's going to be this powerful. So that's what we have. And with that, we can see that this Q bar is elliptic. So this Dotok trick gives us Dotok Ricci flow. And we can now see Dotok Ricci flow as parabolic. So we can now use standard PDE to say that it has a unique solution for a short time. So that is what we have here. So for a given manifold M, this is the talk way of doing that. This is on Ricci flow here. Okay, so we have this from PDE theory. Now the rest now is we are now going to the deformity added to this. We need to convert this back to the original Ricci flow. So in order to have this emitting existence for emitting existence results. And the proof of existence is divided into two steps. Okay, step one, we have to prove the existence of Ricci Dotok flow, which we have explained. That's just the explanation. And then we have to modify the G prime of T, I mean G bar of T of Ricci Dotok flow to get back the Ricci flow. So we need to do that. Okay. So maybe I come back again here. What we have explained so far is that we modified original Ricci flow. Okay. That's the Dotok trick. modifying original Ricci flow using this vector field generated by, diffeomorphism generated by certain vector field, okay, giving us this Lie derivative. We modify the original Ricci flow, and it gives us the torque flow. And the Ricci to torque flow now is parabolic, strictly parabolic, okay? So which means if you are proving existence for Ricci flow, you have to prove existence for Ricci to torque, okay? And that is what we put here, that we prove existence for Ricci to torque flow. Then after we get existence, then we now modify the solution of Ricci to torque flow to get back the original Ricci flow. So the steps are explained here. It's time. So the steps are explained. So okay, this is that to modify. You construct the Ricci flow from Ricci to torque solution. Yeah, do that. Okay. So we just I want us to look at this. Okay, so we claim that G cap. Okay, let's define a new family of metric as this. Then we claim that G cap is a unique solution to this Ricci flow. Okay, this G cap, and G cap is given as this. So we are using psi now, which is another diffeomorphism, not the usual phi that we use here. So to do this one now, to show this, we have to note that we have to show the initial condition. G cap of this is G naught, okay, and it agrees with G bar, yeah, which is the torque Ricci flow. So they start with the same initial condition. And meanwhile, psi here you ask this condition that psi naught is an identity on the manifold. So you can look at this. If you have the evolution of this, that is, you have derivative of G cap is defined as this. Then do this, let's go to 0 with this group. This is a group formula here. You have this. So this is what you have. And from here, yes, this G bar is the torque flow. You substitute the torque flow here, okay, with this condition, and you have this. This is what you have. Okay, I have the next line, because you have this, can be written like this. So we can show that the variation of this, yes, give us this, yeah, which is the Lie derivative, okay, of the pullback of that metric with this diffeomorphism in the direction of find inverse of this, which you have here. So by doing that, these last two terms cancel out. So we have the G cap equals to this. And with that, G cap is equals to this with the initial condition equals to G naught. This is the desired solution of Ricci flow. Okay. So what we have done here is that starting with the torque flow here, you have proved a system for the torque flow. Then you now show that the torque flow pull the diffeomorphism that we added back into the original Ricci flow. So we now say, okay, if you define this with this diffeomorphism here, taking it back, then we show that this is exactly the original Ricci flow. So this G cap defined as the pullback of G, the torque flow. So that is what we have done. This is the system part. Then the uniqueness, is a bit subtle. Yes, it's not so technical, but subtle in a way that you just have to be what type of diffeomorphism that you need to know to show uniqueness, because it depends on the type of diffeomorphism you use. Yeah, you may not, if you start, let me just have some note here. The fact that Ricci the torque flow is strictly parabolic and satisfy the standard uniqueness condition may not be enough to conclude that the solution to the Ricci flow is unique. So it depends on the diffeomorphism, and you can do that. Yeah, well, I have this is the procedure to do that uniqueness. Suppose you start with this is a Ricci flow, and that the family of the homomorphism is a solution of the harmonic map it flow. From here, we know this harmonic map it flow has a unique solution. So it's good. It's a good tool to use in this case. So the homomorphism satisfies that. So a harmonic map is another concept, yes, but which we will not discuss here. So you follow these steps, then GT equals to this is a time-dependent matrix. Yeah, then you claim that GT equals to this is solution of Ricci to Toc flow. Then we show that GT to this is a unique solution of Ricci to Toc flow. Okay, that is what we have here. Suppose we have two solutions, G1 and G2 satisfying the same initial condition, G1 0, G1 bar, G2 bar. Okay, you have two solutions now satisfy this. Then if you take M bar, this M tide, where we are taking the solution Ricci to Toc to be M, so that you have from M to M, choosing this pi I here, which is going to be a harmonic map flow here. Yes, two of them. Then the harmonic map it flow from G1 to G2. Let me explain that. Let me explain that. Okay. Now, if this is harmonic map from M to N, the heat flow for this harmonic map is this. Okay, maybe for us to see. Harmonic map from M, let's say this one is Gij to N, let's say H alpha beta. They may not be of the same dimension. Say this is dimension M and this dimension N. So this harmonic map between these spaces satisfy each flow, and is written as this. This Laplacian depends on G to H, is a type of Laplacian of phi. Okay, so this has unique solution, at least for a short time. So now the point here, and I say, okay, if you take M instead of here, you have M and M of the same dimension, then you define two phi I coming, so phi 1, phi 2. You use phi 1, okay, to pull back G1, you use phi 2 to pull back G2. Then can you show that, okay, if G1 and G2, they are the same from the beginning, the initial value for G2, then can we show that G1 is equal to G2? Okay, so that is uniqueness. Okay. So that is, and we can show that, okay, so G1 will be equal to G2 from here. And this concludes the uniqueness part of the, so that is how to do the uniqueness. So in summary, Ricci flow is not strongly parabolic due to the homomorphism invariance. Then we can get a new flow, which is called the Toc-Ricci flow, okay, by modulo out the homomorphism invariance that cause non-parabolicity in the Ricci flow. You get a new flow, which is now strongly parabolic. Then you can now use existence result from PDE to establish the existence and uniqueness of solution of that the Toc flow for a short time. Then you now convert the results, the solution of Ricci to Toc flow, back to original flow. Okay, so that's what we did. Then for uniqueness, we say for uniqueness, the diffeomorphism you need to use has to be a kind of a unique one in order to have unique solution at the end at the end of your flow. So you can start from the same initial. If you don't use the same diffeomorphism now, then you will not have the same solution. So you have to look for a group of diffeomorphism which satisfy harmonic map heat flow. Okay, we know that harmonic map heat flow has short time existence and uniqueness. So that's what we have done here. Okay. So with this, so maybe in 10 to 15 minutes or thereabouts, let's quickly talk about this last part of today's course, evolution of geometric quantities. As the metric is flowing, then geometric quantities associated with the metric is also evolving. They are also evolving. So Ricci full curvature tensor is evolving, Ricci tensor is evolving, scalar curvature is evolving, volume is evolving. Even the Laplacian, because it depends on time, it's also evolving. So it is unlike when you have the usual heat flow, okay, it's different. But in this case, we are talking about a geometric equation. A geometric equation. What defines this partial differential operator is geometric. It depends on the metric, which we have seen in what we have done today. So now we want to see how some quantities evolve. And the reason is this: later on, maybe by the time we want to do long time, we just talk about short time existence. We want to do long time existence. We need a kind of convergence. And you need to put these geometric quantities in control. You need to develop control on them. The volume of manifold, you need to develop a control. The curvature, you need to develop a control on them so that you'll be able to control the flow and you'll be able to get a kind of a convergence. So it's good that we look at how quantities, geometric quantities evolve under Ricci flow. Okay. And now I will give a lemma, okay, which will help us to do this. We are just going to do computation. So we can see this lemma. So what we want to say here is if the metric GT, okay, which is a smooth family of Riemannian metrics, is evolving in this way. It's evolving in this way. So let's take note of that. This Hij now here is a 0-2 tensor. And you are evolving the 0-2 tensor metric in this way. Okay. Of course, we can just think ahead and look at it. If Hij is equals to -2 Rij, so you have Ricci flow. So that is what we want to do it under Ricci flow, but we just want to look at variation with respect to this. So by the time you do that, and then it will not be difficult to find quantity with respect to -2 Rij. Okay. So this, what we have here, maybe I will do computation of 1 or 2 of them, then we'll leave it. This is metric inverse. This is the way metric inverse evolved. Christopher symbol, okay, evolved this way. Then curvature tensor also evolved this way. Then this is Ricci tensor, evolved this way. Scalar curvature like this, and volume form, the volume evolved like this. Okay, maybe let's look at 1 or 2. So let's have this relation. Okay, let's just look at 1. Yeah, we'll resume there tomorrow. Okay. How does this evolve? If you want to write the metric inverse, yes, I gave that notation. Inverse of this, it is Gij. We'll give that. So we want to see how the inverse evolve, if the metric evolve this way. Now, let's note this from definition. If you have this G, IK, G, AL. Okay, this gives us a chronicle delta IL, so which is constant. So here this is equal to 0 if I is not equal to L, and equals to 1 if I is equal to L. So this is what you have when you do this kind of contraction. Now you can find the derivative of this. So the product rule will give us PIK, okay, this by GKL, then plus the IK so you can with this. And this guy equals to the derivative of this. This is a constant which is equals to 0. And from here, if this is 0, from here you have GKL equals minus GIK. Okay. Now from the definition of this, derivative of GIJ is HIL. So derivative of GKL is HKL. So that's what you have here. From here, GIK here. Okay, if you do a kind of contraction here, let's say you have G, this is KL, have GGL, multiply GGL, and this one by, instead minus here, the same GGL of, I don't want to put at the back, I want to put here GGL, okay? Then it gives this one GIJ, which would be minus G, okay? This one gives us GIK GGL HKL. And I want us to look at the power, the indices here. This gives us minus hij. So that's what you have. So from here, you have T of Gij equals to minus Hij. I think that is okay. You can, what I have on the board can even stop here. But the idea is you have this, and that is that. So that of a Christopher symbol tool, we can do that. And we know the Christopher symbol, I wrote it up the other time, is here. So you can find the derivative of that with this. And we have that. Just maybe let me check what time. Okay, let's check that. We see have time. Okay. Let me just give us, it's a long computation, but we, okay, this is here. Then we want to find the evolution of that. That is time derivative of this guy. Then you are finding the time derivative of this. So which is products, you can use product through product of this and this. Okay. So this gives you half okay. Of course, we know this from definition of the flow. The definition of the flow, we started with this Hg Ij is equal to Hij. So you'll be able to do this one. Then you keep this as constant here. So you have that. Then plus with the derivative of so let's just with this, what you will need to do is that we know this here. Then how do we do this? Of course, this is not time dependent. Then derivative can be derivative of this, derivative of this, derivative of this. So which is in terms of Hij. Of course, that's what you have here. And then you have this one. Then after simplification, we have this. Yes, of course. So this is what we do. And then we use, you work in some local coordinate. If you choose normal coordinates, so that some term like this of G, okay, sorry. Partial high, you have partial high JK of P equals to 0. So if you will get this one in normal coordinates, okay, it's a local normal coordinate. So then when you do that, this is what you will have. You have, of course, sometimes we cancel each other. So maybe because I'm looking at time, Maybe that's going to be a convenient place to stop for today. Once we have this, okay, it will not be difficult to express, to find evolution of this quantity under the Ricci fluid. It will just be like this. So anything we establish here, if you just substitute, okay, like in the case of the inverse that we have like this. So if you want to find the inverse under Ricci flow, just substitute this one with a -2 this. So which will give us this quantity. So we are going to, so that is what we will have. So we will stop here so that we can continue with that. So yes, you may continue here tomorrow, and you can see the kind of metric inverse here. Okay. So we did that. That's what I showed on the board. Yeah, you want to have that. For Liouville Differential connection, we got Liouville Differential connection. This, if you substitute Hij equals to -2 Rij, you have this. Then the volume element is also evolving like this. Then for the curvature, this is a Riemann curvature. We will discuss this one in our next class. Let's just stop here. Thank you.